Hello. My name is Dennis Gannon, and I am chair of this panel session, Cloud HPC, exploring the growing synergy between cloud and high-performance computing. James and I will be asking questions of the panelists. Let me start by just saying who the panelists are. So we have Catherine Yellick of UC Berkeley and Lawrence Berkeley National Lab, Ian Foster of Argonne Labs and the University of Chicago, Jeffrey Fox at the University of Virginia, Kate Cahey at Argonne National Lab and the University of Chicago. This is a great group. A few more words about them. Kathy has tons of experience ranging from managing HPC centers to designing programming languages for parallel computing, and now a partner in running a major NSF program called Cloud Bank to help with cloud access. Ian was a pioneer who conceived of the grid, a network of supercomputer services, which in many ways foreshadowed the cloud concept, and he continues to lead research in HPC and the cloud. Jeffrey has been in HPC business from the early days of MPI and now doing groundbreaking work using cloud-native middleware with MPI to design new deep learning paradigms for science. And Kate is a leader in high-performance distributed computing, and she designed one of the first open-source cloud platforms and now runs a major cloud devoted to academic research for National Science Foundation. Now, I'm going to start by seeing, do we have, is Kathy there?
It seems not.
Oh, well, that's surprising. Okay, then let's start by asking a question of Ian here. Hang on. I'm going in order because that I listed. Ian, what do you see as the main business allocation policy, job scheduling, finance advantages, disadvantages of the cloud versus HPC? Are these fundamental or incidental? I think you might be muted.
I got muted. So there are many differences between cloud and HPC that I'm sure we'll talk about, and we might then debate which of these are incidental and which are fundamental. The thing I'd like to focus on is, at least now, is the following. Of course, you can access computing resources and storage resources on a cloud platform or HCP platform, and you might use different interfaces and get allocated them in different ways. But that seems less interesting to me than the fact that cloud and HPC represent, a sense of fundamentally different view of what services should be provided to users, to people developing capabilities for people, and different views that I think are complementary, not competing. So, cloud in particular can be used for a variety of things, but in my view, the most interesting aspect of cloud is the support it provides for creating and operating highly scalable, highly available services that provide large communities of people with capabilities that they could not otherwise have. And that could be things like always available email or streaming videos or travel recommendations or access to scientific data and so forth. And the way they do those things is, the way that cloud does that is by using this combination of geographically distributed data centers set up to run highly elastic services. And we could go on, but I won't say more about that right now. HPC, on the other hand, is about allowing people to run very specialized, high-performance applications that may be used to investigate fundamental issues in science and engineering, and of course for other purposes as well. So of course you could talk about how would we integrate HPC capabilities into the cloud, and how we might provide some of those scalable service issues in HPC centers. But that sort of seems less important to me than thinking about how can we combine those two different sorts of computing to build new applications. And I think that's going to be a wonderful challenge for the next decade and beyond.
So I see Kathy's here now, and welcome.
Thanks.
What I'd like to do is start by asking you one question to respond to. It's sort of very closely related to what Ian was just talking about. And the question is, do clouds and HPC compete or complement each other?
Well, I think they're absolutely complementary in terms of what they provide. I think that from a sort of, in terms of what you get out of each, I think HPC allows you to run very large scale computations across the full system if you want, or large fractions of the system. For many people, those are things that can be a challenge to do in most commercial cloud settings, even though there are now HPC instances in the clouds, which are, I think, causing them to get to look more, closer from a kind of technology standpoint than they did before. And, with higher speed networks and the ability to do batch scheduling and things like that in clouds. But I think that the really extreme scale jobs are really something not supported on most of the cloud offerings. I think on the other hand that, you do get very high resilience out of the clouds, which you don't get from the HPC systems right now. That's something maybe the HPC systems could work on. But I think that I know that for me, there's a difference between the type of system I want to use in teaching a class, where it's really important that you have that system available, the night before a homework is due. And that's quite different than a research project where I would be willing to trade off, say, some of that accessibility or resilience for larger capability, because I really want to do very large scale computations. And so I think that they really do provide, complementary sorts of features and complementary sorts of, programming and, environments and tools and things like that as well. Although I think we're seeing those move back and forth between the two different instances, with a lot more MPI sorts of capabilities supported in the clouds, and more of the things like, Jupyter hubs being supported at supercomputing facilities and things like that. So I think those kind of technology differences are going to converge more, but I think that from what they offer in terms of the model is complementary.
Thank you. So I'm going to turn next to Jeffrey. Let me ask this one. This is kind of a prediction type question. When will HPC and cloud converge? When will the convergence be so complete that all data system software runs smoothly on both? Such that this panel becomes a tautology. DOE runs an exascale cloud, etc. Is going to happen now? 3 years? Never.
Well, I would say I would hope it happens in 3 years. In that, I guess my current experience is that I'm mainly limited because in fact, a lot of university research is limited because we don't actually have any significant computing capabilities in the deep learning area. Like I had a PhD student who a month ago changed his topic, which was natural language processing, because we couldn't get enough compute time to do the hyperparameter searches that you need to do to get reinforcement learning to work. So I am hoping that in 3 years, we will be able to either use HPC systems, whether they be federal or university, or use clouds and go back and forth. Currently, my dominant use is Google Colab, which is effectively a cloud system. I run much more on that than anything else, although I also use local clusters.
That's really interesting. That's very interesting, Jeffrey. I think now, James, do you want to fire something at perhaps Kate?
So Kate, if I was to pose a question to you, I'm sorry. And so can I ask you the question, do cloud and HPC compete or complement each other?
Complement. So I think that Kathy already spoke to that a little bit. And I think that maybe sort of combining the various insights that everybody else shared, I think that they are fundamentally addressing different usage patterns and support different type of services the users want, right? HPC is very highly optimized towards doing something that is very well defined, running a job. And it does it very well and it does it very efficiently. Clouds, on the other hand, tend to support a wide variety of services, right? So that implies on demand, because you don't know when you're going to get those requests. That implies the ability to configure your own environment. But then once you did that, that also implies that in that environment, you can do many things rather than just run a job, right? You could SSH to that environment. You could configure it further and do many unrelated types of activities. So I think that there are customers on both sides of the question, so to speak, right? There are people who are primarily interested in running large simulations in very optimized fashion. But I think that especially for the emergent applications and for new types of things that people want to do, for investigations that are open-ended, people typically like the sort of the more interactive support that cloud brings with it. And of course, those different sets of services that clouds and HPC support imply different operations models and also imply a different economic model where one of them can operate on a sort of prepaid basis, whereas the other is especially for commercial clouds, whether the other is paid for and operates on a more retail basis, where you can buy a small share in a resource, a timeshare in a resource, and use it for just that amount of time. And of course, there were many demonstrations of combining HPC computations and clouds within the same resource, right? So one example is I operate a bare metal cloud, OpenStack cloud, or modified OpenStack cloud, because it's a research cloud that supports computer science research. But it operates very much like a standard cloud. In other words, you come and you lease the resources for a certain amount of time, run your experiments, and then you go away. And we are currently integrating with Open Science Grid to run Open Science Grid workloads in the background. And we've done something very similar with running not high throughput computing, which of course is Open Science Grid, but with running batch computations in the background, right? We're combining on-demand availability for computations from the Advanced Photon source, which is an experimental facility that needs on-demand, and batch workloads from a mid-scale infrastructure at Argonne. So I think that they are very much complementary. They can work together, and over time, we're seeing a little bit of blending between the two, right? So HPC is adopting certain practices from cloud. So I was saying it's important to have control over your environment. Many HPC installations these days run workloads in containers, for example, so give users some control over the environment. And then with systems like spot instances, for example, cloud is becoming a little bit more like high throughput computing. So there is a certain merging that's going on between those two complementary paradigms.
Thank you, Kate.
So Dennis, let me, if I might, I'm somewhat surprised at the comments from all of the panel speakers. I mean, I would have thought that as a general observation, cloud is the future and everything is going to merge onto cloud. But I'm getting a much different view from our speakers. than that. And so I know we have a little bit of time. I wonder, could we tease at that particular issue? And let me offer some areas to look at. Number one, what are the economics of cloud versus HPC? That would be one question I'd like to throw out. And then this traditional HPC. And then the second one is, I very much understand and appreciate the observation that some workloads you want to do traditional HPC, some workloads you might want to take on cloud capabilities. But if I look forward, I would argue, and I'd be interested in the panelists' views, Dennis, do we eventually have to make all of the two different types of things work together? If training is something that works nicely in cloud, and yet I want to do simulation on a HPC system, when I have to blend the two, do I have to bring together the two technologies and have a common platform? So two very open-ended questions, Dennis, and maybe you could lead off with the economics one, please.
Oh, you want me to lead off?
Yeah, you could lead it off. Okay.
Actually, I was going to turn it to Kathy, because I think the project that she's involved in, the Cloud Bank, is a very interesting one, and I'm not sure people are really that aware of it in the community right now, because it's a really interesting. It's right directly into the economics from the user perspective.
Right. Yeah. Thanks, Dennis. So Cloud Bank is it's an interesting project. I actually sort of inherited it from David Culler, who was originally the Berkeley PI, and it's led by Mike Norman at UC San Diego and Ed Lazowska at University of Washington, and now me. And it's an NSF-funded project providing sort of the provisioning of commercial cloud resources for NSF researchers. And so I think it's a really interesting model. And I think we've learned a lot. It's sort of a pilot project. So we're looking at some of the things that researchers struggle with in trying to use the commercial cloud. So some of it is training and support, which, the HPC centers for the scientific community have always had a lot of somewhat specialized scientific support. So they'll pre-install, for example, at NERSC, when I was director there, and we would, pre-install things like the global climate modeling codes or material science modeling codes, things that are really popular by a large number of users, and tune them to the hardware platform that you're running on. And whereas in the cloud setting, people are sort of on their own. So if you're a really a really sophisticated user from a computational standpoint, and you're really comfortable building your own containerized software packages, installing them on clouds, or you have something that's pre-built as a container, that's a pretty good match. But it can be a real struggle for people that are trying to use kind of raw hardware resources in the cloud. So the training, the other thing is being able to manage your time allocations, and this goes back to the financial model and the incentives, because I think that commercial cloud providers have, even if they give somebody some free credits, you typically have to provide a credit card with that, and they have no incentive to tell you that you have run through your credits and are now charging up a huge bill on your credit card. Right? Their goal is to make money, and that's appropriate. They're for-profit companies, and but it's not something that the research community wants to get stuck with a $20,000 bill because a graduate student went off and maybe even doing useful work, but unexpectedly that bill comes through. So I think that so Cloud Bank is trying to provide some of those kinds of services for account management and things like that, and kind of a portal that people can come into in order to get access to commercial cloud resources. Now, one of the things that we're struggling with, and it's an ongoing conversation with NSF, is the way that it was originally configured. Cloud Bank, when you write an NSF proposal, first of all, it has to be an NSF call for proposals that is part of Cloud Bank. It's sort of Cloud Bank enabled, if you will. And then people would dedicate a certain fraction of their budget to their cloud request in addition to their financial request. Well, that is, I think, breaking one of the fundamental advantages of cloud computing, which is the fungibility of your budget and the ability to say, oh, this year I don't have, one of my graduate students just graduated. I have a little bit of extra money. One of my other graduate students really wants to run this big computational problem. I can go ahead and take some amount of money and spend it on cloud this year. I didn't anticipate that 3 years ago when I wrote my grant, but now it's the right thing to do. Or the opposite, saying, I don't need these cloud resources because I don't have the graduate students. I need to instead use them for a postdoc or something like that, right? If you've pre-allocated your time, your funding that way, then it's, I think, really, doesn't give you the elasticity and the flexibility that you have with a commercial cloud offering right now, if you're just taking some of your grant money and saying, at this point in time, I want to go spend some of it. So that's something we're talking with them about fixing, allowing people to come in and incrementally ask for, sort of in 1 year at a time, sort of increments, ask for computing time for a particular problem that they're planning to work on. I think Canada has a cloud model for research that is closer to that, where it's actually independently funded. So it'd be more like the HPC centers in both NSF and DOE, where it's funded by the federal government, and then allocations of time are made to faculty in that commercial cloud. So I think that we really need to think about that type of model if we want people to be able to use the commercial clouds. And I think there are real advantages to that, but I think it's also the case that sometimes we oversimplify the arguments on the financial model behind the clouds and the HPC systems, which is they're both benefiting from a lot of the economies of scale, right? You've got a fairly large center, you've got tens of megawatts, sort of that for me, that's the easiest way to think about the scale of the center. Okay, so some of the cloud providers are obviously even larger scale, but it's not as though we've got the HPC centers are off buying, individual clusters, a single rack for a single research project. You get system administrators that are handling a large set of resources. And so I think you get a lot of the benefits of that economy of scale. They're buying electricity, power at bulk sort of rates, things like that. So a lot of those advantages are on both sides. The difference is that the HPC centers are not there to make a profit. They are there to serve the research community. And the commercial cloud providers are there in the long run to make a profit. And what we've seen is that, you can say, well, they're making so much profit, surely they would be willing to give us lower prices to do all of the wonderful research that we would like to do. And in some cases, they do make donations of time that are very generous. I think there's many millions of dollars of time being donated from the commercial cloud providers. But we've also seen that they're willing to take that back when they, in things like, some of the other sort of business offerings that used to be very free or very inexpensive for universities, and now they're going to be charged for some of those services. So I think it's really important that we continue to have what I'm going to call them HPC centers, whether they're managed more like a cloud in the sense that people can use them for all different scales of computations. I think that should be the case, that it's not just reserved for the high end, but that we need that to make sure there's still competition and that we don't get into the position where we're at the mercy of the commercial cloud providers in terms of the cost of those systems. So that's why I think they're complementary and they're both very valuable.
Can I speak to this a little bit,
Sure.
Dennis?
Yeah, of course.
Kathy, yeah. So, sort of maybe a slightly different perspective. I think HPC centers have long had a dual role, and this dates back to the first supercomputer centers. They serve as a place that people go to run scientific software of all sorts, sort of like an on-demand workstation. People that don't need a HPC, but it's just convenient and accessible, and then as a place to run these really huge computations that you couldn't run anywhere else. And so the competition point is certainly very valid, but I think one could reasonably debate whether for these small scale things, whether cloud might ultimately be better in many cases, for things for which the actual cost of the cloud is trivial, because you're not using a lot of computing. And the fact you can get rapid access, you don't have to sit in the queue, that's pretty wonderful. Some years ago, someone did a benchmark study, I think it was at TAC, saying how much faster their programs ran on their supercomputer than on the Amazon cloud, and I did this silly little thing. I said, well, what if you take into account the queue time? And of course, it was faster on the Amazon cloud and for these small computations. So an interesting thing then that may happen is if we start to move some of the low-end stuff off to the cloud, what happens to the, if you like, not the business case, but the political case for HPC? You know, a lot of the political support for HPC derives from the fact there are all these long tail people that use them. If we only end up supporting a very small number of high-end users, that might be a potential challenge. So, and then one other point I think which is interesting here is, well, why is it that cloud is potentially better for these low-end things? And it comes down, I think, to speed of access. And the issue is that the scaling issue. So cloud, you know, offers this positive returns to scale. If they get another 1,000 users, well, they can buy more computers and support another 1,000 users. While an HPC center just has 1,000 times more support. Well, not 1,000 times, but has to support the additional 1,000 users, and therefore, in a sense, they have a negative return to scale in an economic sense. And I don't know how we might be able to overcome that problem without charging people for use of resources.
Any other
I can make a few comments.
Well, let me make sure I understand your economic argument about charging people for resources. So I think one of the other sort of problems in thinking about the economics for clouds versus HPC. So first of all, let me agree with you on the very low end, and I'll bring up again the teaching example. And one of the things we're doing both in Cloud Bank and other projects at Berkeley is supporting introductory data science and computer science courses using things like Jupyter notebooks, and you know, where the textbook and the videos and everything are all integrated. And you know, the cost of that per student per semester is under $3 on a commercial cloud. So that and you know that you've got reliability, you've got it's really sort of seamless, and I think it's really does make a lot of sense. Now now, some of the scientific users, each one of them may be somewhat modest, although when you take it in aggregate, for example, there's a lot of modeling, you know, relatively small scale jobs for modeling material science. And you know, I think that's, you know, in aggregate, it still is costing the research community or somebody a fair amount of time if you do that in a commercial cloud. So I think we need to be a little careful about the economics of the commercial offerings when the aggregate amount of computing starts to scale up. And the other thing that we've seen is just the tremendous cost for things like GPUs in the cloud, that they're extremely expensive to use in that sort of setting. So I think there are places where the economics are not so clear, even kind of below the huge scale.
I think I was making a case about, so, you know, it's a resource management. There's always a question of who do you say no to? And so how do you manage excess load? So in HPC centers, you do it by making your queues longer and making people wait longer. And in cloud, you make it by charging people. And so it's
absolutely.
How do we strike a balance between those two approaches, I think.
So I do think you need to push. Oh, go ahead, Kate.
Yeah, I just wanted to jump in a little bit on Ian's point about, in a sense, a lot of small computations sometimes subsidizing large computations. But on the other hand, what's also true, I think, is that the cost of cloud computing in terms of operations is greater. And that, I think, comes from two sources. One source is that you know, inherently you can schedule on availability computations much more efficiently, right? So famously, all those batch-operated supercomputing centers get above 90% utilization, whereas utilization in the cloud, utilization coming from on-demand usage, is actually relatively low, right? And unless you've got something else running on the background, like the spot instances or high throughput computing loads and so forth, it actually costs you money per deployment. But the other source of cost in the cloud is also operations. The clouds are very significantly more complex beasts than batch schedulers, right? I mean, there are security considerations that you have to take into account once you grant users higher level of privilege. You have to make sure that they are on isolated networks. Now you have to configure your center differently. You have to manage the networks differently. You have a lot more moving parts. And I think and so, to illustrate, for example, I'm operating a cloud in an HPC center, which has scheduled downtime roughly once a quarter, right? And there are no provisions made for providing continuous service during that time. So we just schedule downtime on our cloud as well, right? But that means that we can't provide the same SLA as commercial clouds, right? So effectively, we're offering less in terms of availability, right? So that goes into the cost. So I think I like your argument very much, and I think you're perfectly right about that. But I think that there's also
Do you like Kathy's argument or my argument, or both?
your argument about small computation subsidizing large computation.
Jeffrey, you were going to jump in with something.
Well, I wanted to note a couple of things which are sort of related to this conversation. I think the discussion of simulations and data analytics might be a little different, because most data analytics can be run on an individual job can be run on relatively limited resources. And I think everything I do or would conceive to do could be done on 8 GPUs. And if you look, for example, at MLPerf benchmarks, where there are some large GPU clusters, several thousand on an individual job, if we're allowed to use efficiency as a measure, they're incredibly inefficient. Namely, they're operating in a mode which doesn't seem to me very realistic. So and this comes back to this question of Ian mentioning lots of small jobs versus big jobs. Well, I have a feeling in data analytics, it is possibly maybe not tiny jobs, but there are relatively small jobs, which are the basic unit. And you have a lot of them, as I said. To compete with Google on hyperparameter searches, you have to run several hundred or 1,000 hyperparameter runs for every real algorithm improvement. So, but each of those, as I say, at least we would run them on less than 8 GPUs, 8 or less GPUs. And the other comment I would make, I can't afford either machine. I can't afford HPC systems and I can't afford clouds. So that's why I use I either use free local resources or free Google Colab.
Well, actually, that's a great thing to be able to do. I know because I just got my Amazon Web Services bill for the month, which was $70. It surprised me. I didn't think I had used it this month, but that's the way it goes. That gets back to what Kathy said about credit card surprises.
Actually, I got that surprise as well. 7 or 8 years ago, I published a MOOC using Google Course Builder, and that was free. And then suddenly, 6 months ago, I started getting $100 a month bills, which is actually charged to my personal credit card, because at some earlier time, they'd insisted I give a credit card for some peculiar reason, which I did. Now I have to decide what to do. But so that's one danger of these free time from commercial cloud vendors. They can take that time away, and probably should take that time away when it no longer is an economically sensible thing to give it away.
Yeah, I think we're looking at that fairly large risk, which I think the U.S. Funding agencies or even internationally should be thinking about as well. That if there's a lot of time being donated right now, at some point, if that were to disappear, that somebody will either that work will come to a dead halt, or somebody else is going to be paying for it all of a sudden. And so I do worry, as I said, about being kind of at the mercy of the prices being charged entirely, by the cloud providers. Not that that's not also a good source for some of the computing needs. I wanted to, I think, agree with one of the things Kate said about, I think we need a better economic model within the HPC centers. And I think we do over allocate those systems to the point that the wait times, I think to Ian's point, that, you know, the wait times kind of become ridiculous, and, or at least not ridiculous is too strong a word, but they become a, something that it makes the scientists less productive. And if we could set up the economics such that, you know, we use, you know, different charge factors for different queues if you want something to run urgently versus not. But I don't think we do that enough, and probably have something more like spot pricing, which would be like, I mean, we call it at NERSC a scavenger queue for running, you know, jobs that are free or have a very low charge or something like that, so that we can make use of things. But probably those would have to be, that you have to be able to kick them off the system then in order to run the higher priority jobs that are, even if they're not spending real money, if they're spending a higher percentage of their allocation, to get the right sort of behavior that you want within the HPC systems. So I think that there's probably more engineering of those kind of the cloud credit, sorry, the HPC credit models that we could probably get different behavior from.
I mean, if I could raise, I'm sort of mostly raising philosophical questions, not practical suggestions, but, you know, Kate commented that the HPC systems are always 100% used and the cloud is not. But you might also say, well, the cloud is only being occupied by the people who think the computation they're doing is worth the money they're spending. We don't, presumably the computing that's being done on the HPC systems has varying, if one could assign a financial value to it, it has varying values, but we don't distinguish between the ones that are, you know,
so Kate, if I may ask on that same point, you mentioned that for cloud utilization is less, so, and complexity is more for the management. If you're an enterprise, I mean, a large-scale enterprise, if you're a US agency looking to buy compute and you're cost sensitive, are you going to want to pick your own systems or are you going to want to pick cloud? When do you make that choice?
Yeah, I think that depends very, very much on what your workloads are, right? And what types of workloads you want to support and what you're doing. I think that if your users are essentially interested inherently in running large-scale data parallel jobs, right, where noise, for example, noise reduction is an issue and so forth, you definitely want to do an HPC system. Right, you want something that is optimized for supporting those types of jobs. If, on the other hand, you're, for example, supporting, not to stray too far, a computer science research, right, which is the cloud I operate as a cloud for computer science research, specifically built specifically for that, right, and you need things like bare metal configuration, and you need users to be able to allocate specific pieces of hardware to eliminate performance variability, if that's what you're studying, and so forth and so on, right? And you want them to design new operating systems and new virtualization solutions and things like that. You won't be able to support that by submitting jobs to batch schedulers, right? In that case, you definitely are going to need to operate a cloud, right? But there are many cases, you know, between those two extremes. And I think an important, so, you know, the first thing you need to do when you operate any kind of resource is make sure that you fulfill your mission, right? That you support the goal you have. And, you know, that means paying close attention to the goals that you have. If your goal is to support any kind of experimental research, and not just computer science, but let's say any kind of domain science research coming from facilities like the Advanced Photon Source, for example, or like the increasing investment in edge and IoT, which I think will flip the balance towards clouds eventually, personally, right? Which has all those self-driving vehicles and things like that, which place huge emphasis on real-time response. then you will want to support something that offers on-demand capabilities, right? And not only on-demand capabilities, but some kind of moldability of the environment, a large degree of control over the environment. Because you're not going to be just providing compute to those workloads, but you're also going to be configuring networks in a certain way. And that's where you will need that control as well.
Kate, thank you. Good points. I have another series, unless somebody wants to follow up on what Kate said, I have another series of questions regarding the application space and what's going on there. So let me launch into that if no one minds. The thing that I've noticed recently, or at least over the last couple of years, has been some things that started, I would say, in the cloud or the industrial setting, which is having to do with doing very large machine learning models, deep learning models, and that became a really big thing, mostly conducted within the kind of cloud labs, if you will, the industrial cloud labs. But then I started to see some really interesting science applications of this stuff, rather than just identifying pictures of dogs. I started to see things like useful stuff, like identifying images of galaxies, or even a lot of biological applications. And then I started to see this stuff start to migrate to the HPC centers, where some very interesting things are going on. And so I've seen a lot of those stuff. Jeffrey has done really interesting work around taking some of these models and replacing some clunky cloud middleware with some good finely tuned HPC stuff, MPI stuff, and really getting really good performance on some of this. On another side, I'm seeing some other things that are really fascinating, like just the recent issue of Science had a very nice article from the University of Washington about the work that they've been doing on protein folding based on work that was originally in Google on using deep learning to sort of accelerate the ability to do protein folding, which is kind of a breakthrough right now. It's really impressive stuff. And they're using the cloud for that, but they could be probably doing even more in the HPC setting. Biologists finally somehow feel comfortable in the cloud, more so than the physicists. Anyway, any comments about what you see in the application space, the trade-off between HPC and cloud?
Well, as I said, I think I would like to use both. And I also would like to use software environments that have the best features of both. Like I'm certainly going to use MPI or UCX to get decent performance, but I'm also using Apache Arrow, which sort of comes, or Parquet, which comes from the probably the cloud community, and then I'm going to use TensorFlow and PyTorch, which comes from a deep learning community, and lots of things like Pandas from the Python and DAS from the Python community. So we need all those. I think we need to try to provide platforms that integrate these communities together. And then we can look at different business models which may instantiate them either as a formal cloud or a formal HPC center. But I think that you want to take the best technologies from both fields and put them together, because each field does some things very well.
So I agree with that, and I think that what we really want is software environments that are completely portable across HPC and commercial cloud settings, and things like containers that Kate talked about are part of that. But I think it's also, fundamentally the programming models for, let's say, big data analytics, if you look at things like Hadoop and Spark and so on, which have been looking much more carefully at performance issues over the years, but it started from a fundamental assumption that nodes fail all the time, and therefore resilience of my computation is kind of the key design problem. And that led to a lot of overhead in a lot of those implementations that, things like storing data out onto disk frequently, which you could only really afford to do that if you had local disks, made those things not very good fit for HPC systems, but also maybe where the assumptions weren't necessarily a good fit, but also your failure rates are a little bit lower if you don't have a disk attached, by the way, per node. But you know, that I think those are changing and they are converging. But I think what we need is for these software platforms to be something that can easily be moved from one environment to another. And I'll just give one example of that, which is looking at data coming. This is one of Peter Nugent's projects, looking for things like supernova in image data that's coming from telescopes every night. So there is a real-time, you know, kind of constraint associated with that, although not at the rate of a self-driving car. And what they demonstrated is that they could take that stream, that workflow, and automatically, or at least maybe not entirely automatically, but move it from, they were streaming it to NERSC, where it was doing the nightly data analysis, including machine learning algorithms, but then they could move it to, say, another cluster at the lab or to a commercial cloud, so that you can get that kind of resilience that you need and basically use whatever resource it is that's most cost effective for you to use or most available to you at a given point in time. So I think that's very important. And just going back to something you were asking about, Dennis, in terms of applications, I do think we're seeing a lot of convergence with machine learning methods being used in a lot of scientific applications, both to control things like which simulations to run, but also to, you know, improve various sort of data analysis problems for experimental data and so on. I'm going to maybe try to disagree with Jeffrey, though, on one point about the data analysis problems being mostly small. Well, maybe it's the case that most of them are, but in my talk later today, I will talk about using very large scale computations for very large scale data analysis problems. And I think there's a little bit of a, I hate to use kind of lack of imagination in that community, because they're so used to using, and some of these communities, like the biology community that I work with, mostly they're used to doing whatever computations can fit in a single shared memory node. Right. And I think that's happened even to some extent in the machine learning community. I mean, there's certainly multi-node computations, but whereas the HPC community for many years, you know, has been thinking about, well, what could you do with 100 or 1,000 nodes? And so there's different scientific questions you can ask there. So I think there's, you know, it's partly that those computations are constrained because that's what they're used to having resources for. And, you know, that. Anyway, so I think that's, and the last point I'll make on applications, and then I'll let everybody else talk, is, you know, it's really interesting to me as a computer scientist that for most of my career, computer scientists have not needed a lot of computing power. Right? We have not been big drivers of high performance computing. Yes, you know, the kind of systems that Kate talked about, being able to use really unique hardware configurations, being able to crash your hardware because you're studying operating systems or whatever, that's really important sort of test beds. But the largest scale computations have been done by the physicists and the chemists and the biologists, the material scientists, and so on. And but now with machine learning, the computer scientists suddenly have a need for very large amounts of computing, and I think are naturally going to the cloud because of the overlap in that space. But I really think that I don't think we should. I think we should have, you know, that the funding agencies should really be funding research infrastructure for people doing basic science research that's using even deep learning methods of those same kind, but are not necessarily of commercial relevance. And so I think we need a research infrastructure for basic science that will support those computations, including computer scientists. Thanks.
So there's a couple of comments here from the audience that I just wanted to pass on. Manuel Rodriguez says, and this relates to something that Jeffrey has said, a lot of students and researchers are in the same boat, referring to not having the economic resources to do what you want to do. And he says, Google Colab is the only alternative. That's kind of sad, isn't it? Google Colab. Well, I guess if Google Colab is that good, then I've used it too. It is nice, but it'd be great if there's more. There's another question from Hemant Jain, and the question is, how about scalability issues in HPC versus the cloud? So want to address that scalability of HPC versus the cloud. Kind of open-ended, but.
Well, I'll just say we've done a study recently at very small scales that some of the cloud HPC instances are very competitive with HP. But this is HPC systems because they have things like InfiniBand networks and they've got the scheduling capabilities to co-schedule across nodes. But these are at the scale of, say, 4 nodes. These are not large-scale computations. And we are actually trying to run some larger scale, instant problems now across the cloud that have those HPC capabilities. When we looked at this, a decade ago, there was just no comparison. And we've tried running, for example, some of our genomics computations that require very fine-grained communication on a commercial cloud a few years ago, and it was a disaster, but that was a gigabit Ethernet sort of model. And so I think there are particular cloud instances that are starting to provide that kind of competitive network performance, but I don't think that they're anywhere close to the scale that you can get in an HPC center.
Yeah, I think that partly this depends on how you define scalability. So I think that I think it was about a decade ago that Amazon virtual cluster actually got on top 500. It was I remember it was in the fateful 42 position, which is also, of course, the answer to universe and everything. And so, at least for some workloads, and I'm not saying that top 500 is necessarily that the NAS parallel benchmark is the answer to everything. I think that for some workloads, clouds have been performing fine for a while. And I agree with Kathy that those instances and those offerings have been improving. And when you listen to some more recent talks from Amazon and other providers, they're doing wonderful things with GPUs and other things as well, and certainly paying attention to things like single tenancy and all sorts of bypass arrangements to reach the hardware directly and so forth. That still does, however, mean that there is some noise that there might not have been on a large supercomputers, and we probably need to think about that. There are also other definitions of scale, which is how many users can you have and how many different applications or what breadth of applications you can satisfy on one installation, on one resource. And I think that if you define scale differently, I think that for many of those definitions of scale, clouds are actually probably leading. We were talking earlier about the long tail of computations, right? Not focusing on the big hero computation, but paying attention to the long tail. And I think that as far as that goes, as far as that scalability goes, right? So scalability in the users or different types of problems that you can support, clouds are probably much better than HPC.
Maybe a year or so ago, I went, just before the pandemic, I went to this conference called MLSys, which has quite a lot of pretty interesting study of machine learning, mainly on clouds. And I noted that there were papers there which were pretty interesting, which were studying cloud performance. And they were addressing issues specific to clouds, like because your 8 GPU system was not allocated cleanly to a co-located nodes like there would be in HPC. They were scattered around the cloud, and so there was interference in the networking between the users. And so there was a sort of new type of research going on, which I found quite interesting, which I hadn't seen that research in the HPC community. So it's sort of important to know what this model is. If the model is your jobs are allocated in a rather diverse fashion compared to an HPC model, that is maybe that's actually an efficiency issue that is worth considering. Then you have a new set of research issues for Kate's cloud to address.
Yeah. So talking about that issue, I just wanted to go back to the previous question or the previous comment about Google Colab, and just one quick note. we actually, in Chameleon, which again, bare metal reconfigurable cloud, we integrated Jupyter interface onto that. So it's one of the 3 types of interface that we support. So you can now pull up a Jupyter notebook. It's credential integrated with Chameleon, which means that credentials are implicit in your coding cells. You can pull up Jupyter notebook and access Chameleon resources from there directly and write your programs this way. And I don't know if that offers you all the capabilities of Google Cloud, but I think it will go at least some distance towards addressing that.
So I can say one thing about the advantage of Google Colab that I found is that they have lots of really good, especially in the area of machine learning, deep learning, software already there. The libraries are all there. That makes a huge difference, because when I go and try to install the stuff on my own machine or a virtual machine somewhere else in the cloud, oh my gosh, the installation can be, you got to do that. That's software for you, which is required. Let's see, there was another point. It was that I think we covered that thing from the audits. Okay. Another thing I was going to say about the scalability. Kathy mentioned the scalability with the small clusters, and now things like Amazon and Azure, Microsoft's Azure, they have some pretty nice features for deploying, in a very small number of clicks, your own small custom cluster. And I think I've tested it up to sort of like, 8 cores or 16 cores, something like that, and it works, and they're pretty good. And if you really want to, put your muscle behind your credit card, you can have GPUs on those as well. And that's good. One of the most extreme cases I've seen the cloud vendors do is to satisfy the high-end compute customers that really want some HPC in the Azure cloud. Microsoft went out and bought a Cray and put it on the cloud. Now that's kind of an interesting way of approaching convergence, but they did. I've never tried my credit card on that one.
So can I ask the panel? Do any of you see a challenge with cloud in terms of, in traditional HPC, there's been a large effort to be innovative, to push technology, to push leading edge technology, get the fastest machine. I know in some sense it's silly, but it drives technology development really in ways that can cloud do the same, or is cloud going to bury the technology underneath after a while? Are we all just going to be worried about our credit card costs and not so worried about the technology we're running on? Is that a problem or an opportunity for us?
Yeah, I think, I think that there's a lot of opportunity there. In particular, in commercial clouds, I think that the providers are fairly aggressive in integrating new offerings, integrating new hardware in their offerings so that you can access actually probably fairly innovative technology sooner than you would be if you were, contemplating procurement for a data center that you're running, operating yourself. And then, of course, on the other hand, we've got systems like Chameleon that are specifically created, right, to get that innovative hardware and make it available. So I think that as far as that goes, I think that clouds certainly create a lot of opportunity, and I don't think that they will slow things down. I think that supercomputing, to me at least, has always been the place where some sort of holistic pushing of the frontiers was happening, right? So maybe not this or that innovative hardware, but this or that innovative hardware as a means to an end, as a means to getting higher performance or running larger codes in less time. So I think that this maybe there's a little bit less emphasis on this being performance driven in that way, right, to achieve specific goals rather than integrate innovative hardware in your offering.
So, I think there's a huge transition happening in computer hardware right now. And the fact that most of these cloud providers are designing their own processors, and those processors are not going to be for sale. Those processors are going to be offered for rent or whatever you want to call it in their cloud instances. I mean, we've seen this with the TPUs from Google, but they're not the only company that's designing special purposed hardware for their applications, which are going to be largely driven by, deep learning sorts of problems. I mean, I worry that even for the commercial community, we're a little bit too laser focused on one kind of class of algorithms and not worrying about the fact that, if things like graph neural nets catch on, that those really require other types of memory access patterns and things that are not necessarily going to be well supported in some of that hardware. But I think a bigger concern is that is just what's happening with that processor marketplace. And if the only way to get access to innovative hardware is by is through cloud use, then I think that's a serious problem for just kind of the industry as a whole, and includes, I mean, it's very hard as researchers, through the HPC centers, we've often gotten access to test beds with some of the advanced hardware. I mean, for example, pre-exascale platforms and things like that are available now. And to say, well, you have to wait until it's been kind of completely, when the cloud providers have decided that it can be a commercially viable instance, and to let the entire market be driven by that sort of those commercial interests. I mean, to some extent, it always has to be, right? Because you can't afford to design processors if you're not going to have a market for them. But I just worry that the HPC community, which I think has been really good at influencing hardware through just the information about how various applications will run or not run well on various hardware. I think that we've been able to sort of have an influence that's sort of larger than maybe the size of the market for HPC by being very well informed about those algorithm to hardware mappings and being able to inform the vendors about some of those issues. Whereas I think that I don't see that kind of openness at all happening in the cloud space right now. So I think we'll get access to advanced hardware ideas, but I think our ability to drive it will be really limited.
So I would say I agree, Kathy. There's this amazing developments that are happening in both in the accelerator space and in just the custom processor space in the cloud. And right now I think the majority of TPU cycles, tensor processing unit cycles at Google, are probably being used internally. I don't know if you could even get access to a TPU cluster. I think maybe now you can. But there's like 7 or 8 vendors that are building these incredibly specialized, very high capacity, very highly parallel co-processors that are going to start appearing in clouds or just by themselves. They're very impressive, and I think that's interesting. Then there's programmable gate arrays, FPGAs. Those are appearing. Azure has a huge number of FPGAs deployed inside its cloud. In fact, almost every node is now, the networking is run just through the FPGAs. And I know it's available on Amazon as well. And that's pretty general and it's pretty powerful. The trick is, of course, compiling an application for an FPGA. But even that's getting easier, I've been told. And one other thing I would say is that a person I tried to get on the panel but wasn't available is Satoshi Matsuoka, who's been running accelerator-based HPC systems for some time now, and has been doing very well on the top 500 these days.
Maybe I'll just add to that I think that the ARM processor and all the extensions of it, but also looking at things like RISC-V more of an open ISA model, I think are also opening, kind of maybe contradicting what I said before, but I think in that hardware community, there are also opportunities to make it easier to design more specialized processors. FPGAs being sort of at one end of the spectrum in terms of not really redesigning the hardware, but being able to reconfigure it, dynamically for your application purposes, but even being able to design then really more specialized ASICs based on an open instruction set architecture with, modules and things that you might be able to design, hardware design modules that you can include or design your own. So I think that is actually very exciting for the kind of in the hardware research community and the ability to sort of think about innovative research ideas. I think, as I said, the kind of the economic models around cloud and the fact that if we say that all computing is going to happen in commercial clouds, I would really worry about our ability to take advantage of those hardware innovations.
I had a trivial comment on TVUs. I tried to use them on Google Colab by the offered, and I needed support, which I couldn't get. I could not get them to work properly to do parallel deep learning, which is what I was trying to do. So that's actually sort of intrinsic to Colab. It has no support. But as Dennis points out, usually if you just choose GPUs and CPUs, that support is not necessary because their software environment is sort of the best developed.
So, Kathy, you mentioned in your introduction the challenge of providing support and training, etc. Is that a deal breaker? I mean, we've spent many years getting people enabled on HPC and figuring out what the environments look like, and people can come in and work reasonably effectively. But now you want to run on cloud, you have to figure out how to stand up a cluster, you have to do all kinds of really complicated things. How are we going to address that? Or is that a blocker?
We certainly are worrying about that and trying to address it within Cloud Bank. And in fact, one of the focus areas, both on the educational side that is supporting classes, we're supporting these remote classes at, say, community colleges, smaller colleges that don't necessarily have their own internal research groups or expertise, support for research computing within those institutions. And the same thing is happening on the research side. I mean, I think on the research, well, maybe on both sides, if we can raise the level of abstraction so that people are not provisioning their own hardware and trying to kind of build their own instances and install their own compilers and all those kinds of things, that if you look at things that, in the educational, well, on both sides look more like Jupyter Hubs or domain-specific application frameworks, for biology or chemistry or whatever, that I think that would at least reduce the amount of training that has to happen, or, it narrows it to a smaller set of people. But I think it's a big issue. I mean, at the HPC facilities, we have put a lot of work over the years into training. I know there's a big program at Argonne, a summer program to train postdocs and senior grad students, I think. We've had certainly other programs at the other NSF, and my class is remotely offered to a bunch of colleges through the NSF Exceed centers on parallel computing. So there's just, you're right, there's been a lot of effort on it. And I worry a little bit that if we shift things more towards the commercial cloud it's sort of related to Ian's point earlier that the political or whatever support for that training program, which was kind of leveraging the fact that you had a large hardware instance that you were trying to train people to use, that the incentives for that might disappear. And I think that training is really important. And the specialized, it's not just training, it's also specialized consulting services, which is quite different for experts who still get stuck on a particular problem in terms of how to use it. So yeah, we need to make sure that that is preserved, even if people are, whatever type of platform they're using. So you'd like that to be kind of independent. I mean, I'd like there to be this economy that says, you know, you as a researcher, based on the quality of the reviews of your proposal, are given a certain number of credits and you can spend them wherever you want. And that sort of economic market has to be stable then, in the sense that we can take advantage of, say, HPC type of facilities, call it private clouds if you want, whatever, as well as commercial clouds, but that there's also enough support for the training and consulting and experts.
So I wonder if there's any chance that campus computing systems could actually not provide hardware, but just provide support. I tried to persuade people that that was a good model, but I was very unsuccessful.
Yeah, I agree with what Kathy was saying, which, you know, I tend to call a role that makes a resource, like a cloud resource, available for, let's say, domain scientists. I tend to call it a solutions architect. And I think that as we move a little bit lower in the stack, so in other words, as we move to cloud computing, where you get resources that are available, that are fully reconfigurable, and so forth, that then, of course, entails the necessity of such reconfiguration and acquiring skills that go with that. There is a gap between people who just want to come to the resource and use it for a very perhaps specialized purpose, and what the resource providers provide, right? And somebody needs to, or we need to have something that goes into that gap. And to me, the solutions architects that can adapt resources to what your community needs are probably that. But you know, on the flip side, cloud then also does create a lot of opportunity by providing the freedom to support as many applications with potentially conflicting configuration needs and conflicting access needs, as you know, as you'd want to support. So I think that this is something that we definitely should keep track of, and of course, clouds also, because of that openness and freedom, are an excellent training platform for many different paradigms, like HPC and machine learning, and many different other ones as well, right? So I think that we should, in a sense, embrace that change, but also remain aware that there is that gap that needs to be plugged, and that some effort is needed in that space.
So we just have a few minutes left. First of all, I want to relate a comment. Kate, this one make you happy. From Manuel Rodriguez. He says, Chameleon is excellent. The only issue is the GPU nodes are hard to get. And we are using it in our work. We built an image with TensorFlow and works nicely. So anyway, there's a happy Chameleon customer there.
I am delighted that it works for people. It's always fantastic to meet users and to hear good things. And by the way, we're getting more GPUs. They're on the way.
And another question, Parisa Godis asks, how about energy consumption difference? That's actually a pretty good question. But maybe one thing I'm a little bit concerned about, since we have 7 minutes, we probably need to think about, you know, your parting comments to the world about HPC and cloud, and maybe if no one has any parting comments, we can talk about energy.
Yeah, I would be interested in your parting comments. Where do you see us going to be in 5 years? Will we have gotten rid of our HPC centers and be all cloud, or will we have come away from cloud and gone back to our HPC centers? And what do you?
It's safe to say clouds will have more HPC or more accelerators.
Okay, that's a good one.
Standalone HPC could still exist, but I'm pretty certain that the trend for the success of HPC and clouds will continue and then get enhanced.
Yeah, I would agree with that, and I think that cloud, especially cloud understood as on-demand availability combined with some ability to reconfigure resources is going to get a much larger, market share in science, so to speak. And I think that much of it is going to be driven by emergence of IoT and edge computing, which will drive the need for more experimental workloads, and they will drive the need for this kind of capability.
So I would hope that, in 5 years, we won't be just thinking, well, there's two different places you compute that are sort of similar but have different costs, but thinking about entirely new things we can do by leveraging this combination of cloud and HPC, and that's, I think, will be really exciting to see. On energy consumption, I have no idea.
I think I missed the question maybe about where we'll be in 5 years, but I think, for many users, they shouldn't care whether their computation is happening. I mean, for a graduate student, right, it should be happening wherever maybe, the credit card is currently attached or whatever it is, or the computational resources would be. I think it really should be seamless, and that people should be able to move back and forth very easily between the cloud and HPC systems. And on energy consumption, I will say that, the HPC centers, at least, I don't know as much about the NSF ones, but certainly the DOE centers all run at a very low PUE, and typically have access to some fairly green power. So, the energy consumption is basically equal to the amount of energy required to run the computing systems themselves. It's not a lot of data centers, in studies that have been done actually at Lawrence Berkeley Lab over the years and elsewhere. A lot of data centers were, wasting not quite half, but 40% or so of their power in getting it to the computer systems. And I think these HPC centers today also are very well optimized, as are, I think, the large cloud providers too, so that maybe you've got sort of a 10% tax on top of whatever is the amount that is required to power the computer platforms themselves. So I think they're both actually quite energy efficient. Exactly what the energy mix is does depend on where your center is located.
Okay, well, Dennis, maybe it's on us to say thank you to our panel speakers. It's been a very interesting session. I certainly learned things and got viewpoints that I wasn't expecting. So I hope it's true for the whole audience. There's been a lot of very interesting ideas and concepts and questions raised here. So let me thank you, all the panel members. We very much appreciate your time today. And Dennis?
Yes, thank you. I had a feeling it was going to go well when I saw the email exchanges back and forth between the panelists over the last few days. I thought, oh boy, this is going to be a good group. And it is. Thank you all so much. And I know you've had to put up with a lot of email from me nagging you for this and that, but I really appreciate it. Thank you much.
Dennis.
Okay.
Thank you for the opportunity.
Yes, thank you for
Thanks very much.
organizing it.